Hello student, I am Dr. S. L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. So dear student, in this lecture we will see fundamental theorem of algebra. Okay, so in examination there may be the question state and prove fundamental theorem of algebra. So what is the statement of the fundamental theorem of algebra? So statement is given as if p of z is an non-constant polynomial function, then there is a complex number a such that p of a equal to 0. Okay, so this is the statement of the fundamental theorem of algebra. Now we will see the proof of this theorem. So what is the proof? So we have given here p of z is a non-constant polynomial function. Then we have to prove that there exists a complex number a such that p of a equal to 0. Okay, so we have to prove this result. Okay, so to prove this result, so let us we suppose that p of z is not equal to 0. Okay, for all z belongs to complex plane C. Okay, so this function is defined for all the values of z which is in the complex plane C. Now define f of z equal to 1 upon p of z for z belongs to complex plane C. Let us consider equation number 1. Okay, as we have considered p of z is not equal to 0 for any z belongs to C and p of z is analytic on a complex plane C. Okay, so therefore we can say that f of z is a well defined and analytic on complex plane C. If p of z is analytic, so from this equation number 1 we can say that f of z is well defined as well as the analytic on complex plane C. Also, as a polynomial function always an analytic function, we know that every polynomial function is always a analytic function. Okay, so therefore we can say that polynomial function is always analytic function and p of z is not equal to 0. Okay, for all z belongs to C. Okay, so therefore here we can say that f of z is an entire function. Okay, because here f of z is well defined and analytic on complex plane C. So by using the definition of analytic function, f of z is a entire function. Okay, by using the definition of the entire function, we can say that f of z is a entire function. Also, we define limit z tends to p of z equal to infinity. Okay, where p of z is a non-constant. Okay, so therefore by using definition of equation number 1, or we can say that using equation number 1, so put the values of this in equation number 1, or we can say that taking the limit of equation number 1 as z tends to infinity, so equation number 1 can be written as limit z tends to infinity f of z equal to 1 upon limit z tends to infinity p of z, and put the value of this term and put the values of this term from this. Okay, so you will get 1 upon infinity and 1 upon infinity is equal to 0. Okay, so therefore by using the definition of the limit, so here we will use the definition of the limit for every epsilon greater than equal to greater than 0, for epsilon equal to 1, there exists a positive integer capital R such that mod R greater than equal to capital R, which implies mod f of z minus 0 less than 1. So here we will use the definition of the limit for this term. Okay, so this can be written as mod f of z less than 1, equation number 2. Okay, but we have know that f of z is analytic on a complex plane C. So therefore we can say that f of z is a continuous function. We can say that f of z is a differential function as well as the continuous function on a complex plane C. Okay, so if the function is continuous function on a complex plane C, then we can say that that function f of z is also a continuous function on a closed circle whose center is 0 and radius is r, and this circle which is contained in a complex plane C. Okay, so therefore f of z is bounded on a closed circle whose center is 0 and radius r. Okay, so therefore there exists capital M such that greater than 0, capital M greater than 0 such that mod z less than equal to r. So which implies mod f of z less than equal to m for every z belongs to closed circle whose center is 0 and radius r. So let us reconsider equation number 3. Okay, now we have to choose the maximum m. Okay, so let us, if m dash equal to maximum of 1f, then equation number 2 and 3 we can say that mod f of z less than equal to m dash. Okay, from equation number 2 and 3 we can say that mod f of z less than equal to m dash for every z belongs to C. Okay, so therefore f of z is bounded on a complex plane C. Okay, so therefore f of z is a bounded entire function. So by using the Lewis theorem we can say that if the given function f of z is bounded on an entire function, then that function must be the constant function. So therefore by using the Lewis theorem f of z is a constant function. So therefore from equation number 1 we can write as f of z equal to 1 upon p of z. Okay, so which implies p of z is a constant function which is defined on a complex plane C. Okay, so which is a contradiction to our assumption. Okay, so we have chosen p of z is not equal to 0, but here we got p of z is a constant function which is defined on a complex plane C, and which is a contradiction to our assumption. Thus our assumption p of z is not equal to 0 is wrong, and hence we can say that there exists a complex number a such that p of a equal to 0. Okay, so this is the fundamental theorem of the algebra in a complex analysis. So this is the complete proof of the fundamental theorem of algebra. So you can see, so this theorem may be asked in examination. Okay, now we will see the second theorem that is in the form of corollary. Okay, so if p of z is a polynomial and a1, a2, am are the its 0, okay, its zeros with aj having multiplicity kj, then we have to show that p of z equal to c, z minus a1 power k1 plus z minus a2, or we can say that multiplicity k2 and so on, z minus am multiplicity a km. Okay, for some constant c, and k1 plus k2 plus and km is a degree of the p of z, or we can say that, okay, multiplicity by using definition of the uh, zeros of analytic function having multiplicity. So now let us see the proof of this corollary. What is given? So we have given that p of z is a polynomial with zeros a1, a2, am with a multiplicity k1, k2, am. So from this given we can write this. Okay, so therefore by using the definition of the zeros of analytic function with a multiplicity, okay, so as a1 is a 0 with a multiplicity k1. Okay, so therefore by using definition of this multiplicity, zeros of multiplicity, there exists an analytic function p1 of z such that p of z equal to z minus a1 multiplicity k1 into p1 of z. So here p1 of a1 is not equal to 0, equation number 1. Okay, so by using definition of the zeros of analytic function with the multiplicity, okay, also a2 is a zeros of p of z with a multiplicity k2. So this can be written as p of a2 equal to 0 by the definition. Okay, so put the value of p of a2, that is a2 minus a1 k1 p1 p1 of a2. Okay, equation number 2. Okay, so from equation number 1, so from this we can put the values of p of a2. Okay, so what is p of a2? That is a2 minus a1, suppose that z is a2 minus a1 power k1 into p1 of a2, okay, equal to 0. So but a2 is not equal to a1, so therefore p1 of a2 equal to 0. So this will become p1 of a2 is equal to 0. So hence we can say that z equal to a2 is a 0 of the p1 of z. Okay, a2 is a 0 of the p1 of z. So therefore there exists a polynomial function p2 of z such that p2 is defined as z minus a2 power k2 into p2 of z, with p2 a2 is not equal to 0. Okay, so by using this value in equation number 1, okay, so this is the p1 of z. So put the values of p1 of z in equation number 1, in this equation number 1. So equation number 1 can be written as p of z equal to z minus a1 power k1, z minus a2 power k2 into p2 of z. Okay, so in this way we can find out the for the n term. Okay, so repeating this the process for a3, a4, a4 and so on. So we get last term is p of z equal to z minus a1 power k1, z minus a2 power k2, z minus am power km into pm of z. Okay, equation number 2. Okay, so in this way we can write these steps. Okay, but we know that the last steps of the polynomial function pm of z must be the constant function. So this must be the constant function, because because the non-constant polynomial by the fundamental theorem of algebra, if it is a non-constant polynomial, then by the fundamental theorem of algebra it must at least 1 0. Okay, so by equation number 2, we can say that the zeros of the pm of z will be 0 of the p of z, which is also a non-constant polynomial, because p of z has only nth zeros a1, a2, am. Okay, so therefore from equation number 2 we can say that pm of z must be a constant function by using the theorem of fundamental theorem of algebra. Okay, so instead of pm of z we will replace that is c. So therefore from equation number 2 we can write p of z equal to c, z minus a1 power k1, z minus a2 power k2 and so on, z minus am power km. Okay, so which is the required result. Moreover, here the degrees of the RHS, here the degrees of the RHS k1, k2, km, which would be the degrees of the polynomial of p of z. Okay, so this is the uh, very important theorem or corollary on a polynomial function. Okay, so this is the another theorem on a polynomial. So prove that the zeros of analytic function which is isolated, and this can be also stated in another form. Okay, so this is the second theorem on a polynomial function. Okay, so if you see the proof of this theorem, you can easily solve if you go through the from equation from theorem number 1 and theorem number 2, zeros of the analytic function, then you can understood this theorem. Okay, so what is the next theorem? Prove that zeros of analytic function are isolated, or this can be stated as if f g to c is analytic and non-constant a belongs to g and p of a equal to 0, then there is a capital R greater than 0 such that open circle whose center a radius are containing in G and f of z not equal to 0 for 0 less than mod z minus a less than r. Okay, so we will see the proof of this theorem. So what is the proof? So we will prove this theorem. Okay, so we have to show that if f g to c is analytic on a region G, z equal to a is the zeros of the function, then there exists capital R such that f of z is not equal to 0 for every z belongs to open circle with a center a radius r which is containing in G. Okay, so let us suppose that z equal to a is the zeros of the function f with a multiplicity m. So therefore by using the definition of the zeros of analytic function with a multiplicity m, there exists another function, that is analytic function g of z. Okay, so this can be written as f of z equal to z minus a to the power m g of z, and where g of a is not equal to 0. So let us consider equation number 1. Okay, so here g of z is analytic on region G. Okay, so therefore we can say that this g of z is also differentiable function, and differentiable function is a continuous function. So therefore g of z is a continuous on a region G. Okay, so if g of z is a continuous function on a region G, then we can say that g of z is also continuous at a point A belongs to G, and where is a point in the region G. Okay, so therefore by using the definition of the continuous function, for every epsilon greater than 0, there exists delta greater than 0. Okay, so here we will choose epsilon is mod g of a upon 2, such that mod z minus a less than delta, which implies g of z minus g of a less than mod g of a upon 2. Okay, so this can be written as, which implies mod g of z minus g of a less than mod g of a upon 2 for z minus a less than r. Okay, so this can be written as minus mod g of z minus g of a greater than minus g of a upon 2. We can write in this way. Okay, now prove this theorem, let us we consider the term that is mod g of z, and this can be written as mod g of z minus g of a plus g of a. We can write in this way. Okay, so by using the definition of the absolute mod, by using the property of the modulus sign, so this can be written as mod less than equal to mod g of z minus g of a plus mod g of a. Okay, separating the mod. So this can be written as, by equation number 2, put the value from equation number 2, mod g of a upon 2 plus g of a. So we will use the equation number 2 for this. Okay, so which can be written as, if you take the addition or subtraction for this term, you can write mod g of z greater than mod g of a upon 2. Okay, so therefore mod g of z greater than mod g of a upon 2 for z minus a less than delta. Okay, so which implies mod z of z greater than 0 for z minus a less than delta. Okay, so therefore g of z greater than 0. Okay, so for delta equal to r, for delta equal to r, where 0 less than mod z minus a less than r, we will choose delta equal to r. So therefore that is f of z is not equal to 0 for 0 less than mod z minus a less than capital R, and hence we can say that, okay, so we have proved this, f of z is not equal to 0, and hence we can say that zeros of the analytic function are isolated. Okay, so in this way you can solve this problem, or this theorem of zeros of analytic function, okay, are isolated. Okay, so this is the complete proof of this corollary, or we can say that theorem. Okay, so in this way we have completed zeros of analytic function and polynomial function theorems and corollary in this lecture, and with this lecture we have completed unit number 1. So in next lecture we will start unit number 2. Okay, so we will start unit number 2 from the next lecture.